Okay. Good evening, great afternoon, everyone. My name is Mike Bloom. I'm the current president of SEPM, and my function here today is to introduce our luncheon speaker, Kyle Straub, who is currently associate professor in the Department of Earth and Environmental Sciences at Tulane. Kyle has a very distinguished publication record. He received his bachelor's degree at Penn State in geosciences, and then his PhD in geology and geochemistry at MIT, where he started down a track of working on experiments and sort of numerical analyses of depositional systems. He's going to talk to us a little bit about that today. Since this is an SEPM event, I would like to also say that Kyle has received the James Lee Wilson Young Scientist Award for SEPM, and he also received the Outstanding Paper in Journal of Sedimentary Research in 2009 for compensational stacking of channelized sedimentary deposits. Without further ado, I will let Kyle get started here, and he's going to talk to us a little bit about how it is, how it's difficult to recognize what's going on in the stratigraphic record. And with that, Kyle.
Okay, thank you very much, Mike. Thanks for the invitation to give the talk today. And thanks to SEPM in general for all that the foundation does to help our discipline. So I'm going to switch over here and try to share my screen. Let me do this. And I'll launch my talk for the day. Let me get my laser pointer going. Okay, so again, thanks to everybody who's showing up for this talk. Today, basically what I want to move forward in discussing is challenges that we have in either knowing how time gets stored within the stratigraphic record, or how signals of environmental change get stored within the stratigraphic record. And what I'm going to focus on in some ways is the fact that the stratigraphic record is imperfect, and it's imperfect for a number of different reasons that have to do essentially with the way that Earth's surface processes operate in sedimentary basins over timescales in which we are accumulating sediments. So as I move through the talk here, I'm going to be showing a number of pictures of different collaborators that I have. So in a lot of these spaces that I have up here, you'll see further on in the talk. But for me, it's sort of similar to all or the majority of science these days, in that it's a collaborative effort. And so I've got a number of really great colleagues who are faculty at different universities around the country and around the globe, and I've had also the privilege of working with a large number of really great students, and I'll try to highlight some of their work today. A lot of the discussion that we'll be moving through in the talk today will be centered around ideas that I recently published in a review paper that was put together for AGU's 100-year anniversary celebration. And so for this centennial, they put together a number of grand challenge papers, and I was asked to write one of those papers. And so with a number of colleagues that I have up here, we put together this paper that was published earlier this year in the Journal of Geophysical Research, Earth's Surface. So if you want more information about the talk that I'm going to be giving today, you can find a lot of that in this paper that I'm referencing here. So let's just get into the topic at hand. A lot of my research interests really center around understanding what I refer to and what my colleagues refer to as the stratigraphic filter. And the idea basically here is that you have operating on Earth's surface at any time a myriad of different dynamical processes. These processes that are happening on the Earth's surface, maybe you could think about the movement of ripples or dunes in a river channel, avulsions of river channels, creation of submarine fans. All of these surface dynamics that are going on are influenced by a number of different processes. Some of these processes are internal to a sediment routing system, and we might refer to these internal dynamics as autogenic processes. But there are also things that influence how a sediment routing system moves around that come from maybe changes in the environment or changes in the tectonics in any system. Now, in a site where you're having net accumulation of sediment, all of these dynamics that are going on the surface do not get transferred into the stratigraphic record. There is a filtering process that occurs in which only certain aspects of these processes or environmental signals get transferred over to stratigraphy. So as an example of that, I'm going to show here a movie that comes from my lab at Tulane. I'm an experimentalist primarily, so you will see a number of experimental movies today and data that comes from laboratory environments. In this movie that I'm showing right now on the slide, we have an infeed of water and sediment that's coming into a basin at the top. This basin is a couple of meters in length, about 3 meters in length here, from the entrance to the shoreline. And we are feeding a constant rate of water and sediment into the basin, and sea level is coming up at a constant rate to mimic subsidence. And for the conditions that we have here, we basically have a braided river system that's moving around the basin with channels that have certain relief to them, depths of the channels, certain widths. But what we can do, and what we have done, is also take a look at what is left behind in the stratigraphic record. So here I'm showing a cross section, a strike section across the basin, and during this experiment, every 2 minutes, we collected topography information about how the system was evolving, and we could stack all that topography data to look at representation of the stratigraphy that is left behind. And one thing that you might see when you look at the strat here is that it's dominated by a lot of these large channel scours. And those scours are actually more preserved in the stratigraphic record than they are present on the Earth's surface at any one time period. Sort of mundane conditions of the floodplains, or the overbank environment, I guess you could call it here, do not get transferred to the record as preferentially as the channels. So there's a filtering process that's occurring here. So we want to understand that filtering process. I'd like to understand that filtering process for how it influences how time is stored in the record and how environmental signals get stored in the record. And I'm going to pitch a lot of this conversation today. I'm going to pitch sort of thinking about these problems on one specific problem that the community is spending a lot of time thinking about right now, which is the Paleocene-Eocene thermal maximum, a time period over 500 or over 50 million years ago, in which we had rapid global warming induced by a rapid release of carbon into the atmosphere. And so you can imagine, or you can think, why we might be interested in that right now. So there's a large number of sites here with the stars that are showing where we have records of the PETM. But just to give everybody a little bit of info here, the PETM was an event that lasted about 200,000 years, where we had this rapid onset of an increase in carbon in the atmosphere. Carbon was high in the atmosphere for some time period before it fell out. And as far as the stratigraphic record is concerned, specifically maybe in sites like basins in the American West, what we see for the record here is during the PETM itself, oftentimes what we will see are very sandy deposits, whereas before and after the PETM, we have some channel bodies preserved in strata, but a lot of overbank deposition. So we want to understand essentially how this change in our environmental conditions influenced what is left behind in the stratigraphic record, partially so that we can actually invert the stratigraphic record to understand what was going on in the climate system. So we're going to look at a number of different problems, and we're going to relate it back to the PETM. But I'll start here just talking about the first question, which is, how is time stored in the stratigraphic record? And so here, what I'm going to emphasize this to start with is really the first person who quantitatively showed how complete the stratigraphic record is was Pete Sadler in a publication from the early 1980s, in which Pete essentially noted that what you find for an aggradation rate, think about this as a deposition rate in a sedimentary basin, what you find for a deposition rate is strongly tied into the amount of time that the measurement was taken over. For example, if you were in a river monitoring a dune passing over some measurement rod, you might see an incredibly high deposition rate for a short time period. But if you measure maybe, for example, a deposition rate from biostratigraphy in the Mississippi Depot Center, you're going to get a much, much lower deposition rate than you would find measuring those ripples moving past a dune that you're monitoring in the river. And the reason for this inverse relationship between aggradation rate and averaging time has to do with the inclusion of hiatuses in the stratigraphic record. Essentially, the longer your averaging time, the more likely you will include things like hiatuses, stratigraphic hiatuses resulting from either periods of non-deposition or episodes of erosion that might remove some previously deposited sediment. So combined, these two ways to create stratigraphic hiatuses reduce the completeness of the stratigraphic record and give you this inverse relationship. And we can note on here as well, it was later noted by Doug Jeromack working with Pete Sadler, that there's actually some interesting shapes to sort of this relationship that we have here that we'll talk about more in a second. So I just want to demonstrate this in a lab setting. But one final thing here that I wanted to mention about this slide. This has important implications for how we are able to interpret the stratigraphic record. For example, it makes it very, very challenging to take deposition rates that we have maybe measured over historical time periods where we have historical records and compare them maybe to deposition rates that were occurring, say, in the Jurassic or Cretaceous, whatever time period you like. Because the averaging time of our records deep in Earth's history is much, much larger than maybe the averaging time of our historical records. And that makes it challenging to compare the two to one another. So just to show that this effect actually does occur in a system that you can watch and monitor, I've got another laboratory experiment here conducted by two of my graduate students in my research group. Again, we are feeding water and sediment at a constant rate into the basin and raising here sea level at a constant rate just to create accommodation that is being created at a rate equivalent to how much sediment we are putting into the system. So in a long-term sense, the shoreline does not move, but you can see that there are very interesting dynamics that are going on in this system, what I would refer to as autogenic dynamics, because they are purely internal to the sediment routing system. And so what you'll see here is some locations on the delta at some time periods are receiving no sediment, while others have channels moving over them. And also these channels, as they sweep across the surface, can do erosion. So you're creating stratigraphic hiatuses. Now, if we actually take measurements of the deposition rate, and we do this measurement of deposition rate over different averaging time periods, we create an effect that is very analogous to the Sadler effect. Here, I'm balancing our measured deposition rate by the expected deposition rate, which is our long-term rate of generation of accommodation in the basin. So you see a power law decay here in our deposition rate until we reach a critical time scale here that we refer to as a compensation time scale. But just to emphasize here, these high deposition rates are measured deposition rates maybe that we are getting once an hour. They're deposition rates averaged over an hour, whereas this might be a deposition rate averaged over 50 hours. Now, this compensation time scale that I'm non-dimensionalizing the x-axis with is going to be a critical number for us for the entire talk. It's going to be critical to thinking about how time and signals are stored in the stratigraphic record. And basically, that time is equal to a depth of the largest roughness features that might exist on any sediment routing system at a given time period. Maybe here, this is the depth of the channels that are crafting our strata. And we're dividing this here by the long-term aggradation rate in the basin. For sedimentary basin, this might also, you could think about this as being equivalent to what the subsidence rate might be in the basin. So if you take this, this channel depth and divide it by a subsidence rate, you get a time. And what we find, in essence, is that we see this Sadler effect as you go from small times up until a compensation time scale. And then after that, the rate goes constant on here. Here, the rate goes constant because the only processes removing sediment from this record are autogenic processes. In Pete Sadler's data set, this curve does not go completely flat on here because there are actually also things that are not autogenics going on in the real world. Things like the creation of the Great Unconformity within the Grand Canyon are very large, what we might refer to as externally driven events or allogenic events that affect the shape of this plot. So the point here is that we can predict where we transition from the Sadler effect to a portion of the Sadler effect that is not influenced by the autogenic dynamics purely by this time scale. Now this time scale, I just want to link this again back to what we think about with the completeness of the stratigraphic record. So Pete Sadler put together his database on deposition rates as a function of the averaging window because that's commonly what we can measure in the field. It's hard to actually really measure in the field how complete the stratigraphic record is, maybe say at time scales of a minute. You would need excellent geochronometers for a very, very long time period. But again, what I'm stating is that that Sadler effect is related to the stratigraphic completeness in a basin. So to show this here, basically think about having some stratigraphic record where you are standing maybe at one spot in a basin and you are observing how that one spot in the basin, as you go forward in time, how that one spot is changing in elevation. There's going to be some time periods here of deposition, some of erosion, some that we might refer to as stasis here. And if you discretize this record at a very fine time scale, maybe all of these tiny little dots here, you have some reading of what's going on. What you'll see is that you will get some time periods here where nothing is occurring and no sediment is preserved in the stratigraphic record because of that. And so the record is only somewhat complete. Only these time periods where this curve is going up is the record complete, but all these other time periods it is incomplete. Now, Pete Sadler and David Strauss related this to the time scale at which you, how complete the record is. This completeness is related it's also related to the averaging time scale that you are putting on your record, basically the time scale at which you are discretizing the record. So let's assume rather than a really fine time scale of discretization, maybe we only have information recorded once at each of these red dots on here, right? So our time scale of discretization is coarser. Here, going from this dot to this dot, the record is complete. In fact, as you go from each one of these dots, there is some sediment preserved in between the different dots that you were looking at. So the record becomes 100% complete. And the idea here is the larger your discretization interval, the more complete your record might be. So to show this for some experimental data to everybody, we'll show this with some experimental data, and then in a second, we're going to try to draw some implications for this for the PETM. But again, we have this experimental data from a deltaic system in my lab, in which we are measuring the topography at a very, very tight time resolution, very high frequency. So we're able to take maybe this cross section here, and we can piece together a stratigraphic strike section in which we know basically when every particle of sediment was deposited. Here, the time at which that sediment was deposited is colored by this color bar down here. Now, again, we were able to calculate a Sadler effect for this data, but we can also go in now with different time scales of discretization. We can measure how complete the record is, right? If we average here at this very fine discretization interval, the record is incredibly incomplete, maybe only 10% complete here. So 10% of the time steps of the evolution of this system are recorded within your final record. But if you go to a discretization time window here, equivalent to the compensation time scale, all of a sudden the record is 100% complete. So we're going to try to think about this now, the implications of this for the Paleocene-Eocene thermal maximum. And to do this, we can start off thinking about, okay, what are typical compensation timescales for field scale systems? So on here, I've got a plot, and what we have here is the x-axis being a long-term deposition rate for a sedimentary basin. And there are some spans of different deposition rates that you could think of related to the subsidence rates, either in passive margins, foreland basins, or pull-apart basins. And so we've got that for our x-axis, and here on our y-axis, we might think about the roughness length scale, or again, think about this as the depth of the channels that are crafting your strata. And if we combine this deposition rate with our roughness length scale through this equation here, we can find basically what we find for typical compensation timescales. For example, a passive margin where you have a 10-meter deep channel might have a compensation timescale about 100,000 years, which is pretty long, right? So it means your stratigraphic record doesn't go to 100% completeness until you are averaging the record over 100,000 years. Now, our Paleocene-Eocene thermal maximum, just a reminder of the time scale of that event, 100 to 200,000 years. And also, there are many proposed shorter hyperthermal events that we're not going to spend a bunch of time today talking about. But just note that in addition to the PTM, there are other warming events that might even be over shorter timescales. So just an indication here of our ability to measure this for some field systems. Here's 3 different field systems from around the world, 1 in Spain and 2 in the US West. And we can do a good job of actually coming up with estimates for these compensation timescales from real field systems, right? Because all we need to know are the depths of the channels that are crafting, channel bodies that are in the strata as a proxy for the channel depths that were on the surface crafting the strata. And we need some knowledge of the long-term deposition rate in these basins, which often we are at least able to get an estimate of this long-term deposition rate. So here, the note that I'll make for many of these systems, the compensation timescale here is shorter than the PETM. Okay, we've got compensation timescales that might be 10,000 up to 100,000 years, whereas the PETM is a little bit longer than that. Now, we'll talk about some implications for that in a second. But one of the first implications that I want to talk about here is thinking about this incompleteness and what it means for our ability to actually to estimate time within the stratigraphic record. Think, for example, here, one spot within a sedimentary basin, and maybe that spot in the sedimentary basin, if we think about how it moved forward in time and accumulated sediments here, that one spot in the sedimentary basin, we might only have a date maybe at the base of a formation and a date at the top of the formation. And so maybe for that basin, we are just going to assume a linear age model between our 2 dated horizons. Now, in our experiments, we don't have to just think about time that way. We actually have knowledge of the deposition at every time period within the course of the experiment. So what we can do is compare our linear age model here to the actual age of the strata. And for every time period going forward in this experiment, we can calculate actually an age error between our known ages and the linear age model. Let me see here. What we're going to do here is we're going to normalize our age errors, this time of our age error. We're going to normalize that by our compensation time scale. And we're going to do this for 2 different experiments that we did in our lab. And these 2 different experiments evolved in a vastly, vastly different way. Okay, one experiment here evolved very, very slowly over about 1,000 hours and was associated with channels that just avulsed over the surface. The other experiment evolved over just tens of hours and was crafted through braided channels moving over the surface. Now, when we do the age errors, our age errors here that are normalized by the compensation timescale, which that compensation timescale varies in the 2 experiments, we get a very, very similar PDF for these 2 experiments of our age errors. So that sort of, to me, gives a little bit of faith or belief, I guess I could say, or hypothesis would be the better way to say it, that this distribution is somewhat applicable, or that this distribution shape is somewhat similar in many sedimentary basins if you normalize your ages in the appropriate way. So what does this mean for the PETM? Well, if we take, for example, maybe in the Bighorn Basin in the US West, where we know the channel depths here and we know the long-term aggregation rates, we can take our dimensionless age error and actually turn that into a dimensional age error. And what this suggests on here is, it's quite common, would be quite common for us to be dating our sediments wrong by maybe 15,000 years, or maybe a 2 sigma error here would be 30,000 years. So we've got maybe age errors if we're trying to just take dated horizons at the base and the top of the PETM and try to figure out where we are in this record as far as where we are during the evolution of the PETM, just from a linear age model, because we don't have better geochronometers. We might at any point in this section be off by 30,000 years. So there's limits on how fine we can really ask questions of what's going on in the PETM. So that was question 1, basically making the point that this stratigraphic incompleteness brings age errors into our analysis. Question number 2 is going to be looking at how proxy records might be stored within stratigraphy. And here, think about maybe as climate is changing during the PETM, there might be attributes of your sediments that are geochemically altered, that are being altered by maybe what the climate is like. For example, storing different carbon isotope values within your stratigraphic record. So let's imagine here that we have one spot in a sedimentary basin where time is moving forward and the system is evolving in its elevation, right? You've got periods of deposition, periods of erosion maybe going on. And this unsteady evolution of your topography is sampling some type of climatic signal that might be nice and smooth like this, right? So we're going to sample in this sediment the geochemical information associated with the climate by altering the sediment, but only sediment that gets deposited during certain time periods of this record will ultimately be preserved. So if we take this jagged up and down curve that we have here and we sample it for what's going on with the climate variability, what we're actually left over in the stratigraphy and the schematic that I have here is just a very poor representation of what actually happened in the climate. So we want to know really how accurate can you get from looking at proxies within strata. So to look at this, I'm going to give you 2 case examples where we actually do this problem in laboratory experiments of having strata that is evolving sample a climate proxy. So let me start up a movie here. What we're going to be showing in this movie is a stratigraphic cross section that is evolving through time. It's again a basin where you have channels that are moving over a deltaic environment. But as they move over this deltaic environment, the sediment that is getting deposited is sampling through a proxy. It's sampling this climatic signal that I'm just representing as a sine curve. Now here, for this situation, the climate is varying slowly enough that you can see banding in the strata here that is fully represented by what was going on in the climate, right? There might be hot periods here of hot colors that are clearly separated from the cold periods with hot periods above it. You could imagine taking a core through the sediment, sampling the proxies, and being able to see all of the ups and downs. That's a good scenario. What I want to highlight, though, is that that's not always the scenario. Here, what we're going to do is rather than just vary maybe the climate slowly, we're going to vary the climate in a way that will be scaled off of our compensation time scale. So the movie that I just showed was a situation in which the climate here was changing with a periodicity that was twice the compensation time scale of the basin. But at the top here, we have climate that is varying at a period that is actually half of the compensation time scale. And if you maybe think about taking a core through this record and sampling some proxies to try to find out what was going on with the climate, good luck. This is some pretty messy strata as far as being able to pull out the real climate signal from this 1D record. And so we can show this here in a more quantitative fashion by running time series analysis over the climate proxies that we are extracting from the basin here. And we can show basically that these time periods where the climate is varying fast, we can't find our imposed signal. Whereas if the climate is varying slower than twice the compensation time scale, we're able to pick up the signal in the strata. Okay. In a way, this is a really nifty example of a Nyquist sampling theory problem. And so what we refer to this as is the stratigraphic Nyquist frequency for a sedimentary basin. And again, it's linked into this compensation time scale that I think is actually something that one can measure in a sedimentary basin to think about the fidelity that you should expect of your record. Now, I'll note again that PETM, many of the PETM systems that we looked at, the climate was varying more than twice the compensation time scale. So you should expect to see the proxy records stored in that strata. However, you might think about asking questions of a finer scale from the record. For example, there's been discussions with the PETM of a pre-onset carbon release that occurred prior to the main body of the PETM. There might be, or there's evidence for some pre-onset excursions. But these occur over a relatively short time scale, maybe only over 2,000 years. So in some basins, you might see this, but you're not necessarily going to see it in all basins because that time scale of that event was shorter than the compensation time scale in many PETM basins. So the third question that we're going to be after here, take a pause for a second, but the third question we're going to be after is maybe in some basins, you have a pretty complete stratigraphic record, but you're still not seeing signals. And why might that be? This comes down to an idea that was published on about 10 years ago of signal shredding. So I'm going to try to explain the idea behind this right now. Imagine some sediment routing system here where you put in a clean signal at the top of your routing system. That clean signal might be variations in sediment supply associated with variations in the climate or the uplift that was going on in your hinterland region. That signal, though, might get shredded as it is routed down your sediment transport system. And the shredding that we're talking about here is the deposition of sediment that is making its way down the system temporarily in things like point bars or dunes or in the floodplain. So some of the sediment that's routing down the system here temporarily gets stored in geomorphic forms before it is later released back to the sediment routing system where it might get deposited in a sedimentary sink. And because of this temporary storage and release, the record that you input at the top of the system might be noisy for what comes out the bottom of the system. However, sometimes you do get a clean signal that is able to route its way down the system, and you can actually see it at the end of the system. And so Doug Jeromack and Chris Paola put together some ideas about why that might be. And essentially their idea is that signals can get through the routing system if they occur over time and space scales that are longer and larger than the largest autogenic events that go on in your sediment routing system, the largest types of avulsions maybe that are going on in the routing system. So this is a testable hypothesis for us, and we can think about this with the PETM. There are some locations in the PETM where we think that there was a dramatic increase in the sediment supply during the PETM. So maybe it impacted the shape or style of your deltaic environments. For example, here, a location is being worked on the Atlantic margin. So we ran some experiments on this in my lab with a PhD student, Stefan from Liverpool, and his advisor, Rob Duller. And the idea here is that if you have a sediment routing system, even when this sediment routing system is just experiencing constant forcings, a constant supply of water and sediment to the basin, deltas don't remain a constant size. There are fluctuations associated with avulsions and reorganizations of the transport system that cause the system at some time periods to efficiently pump sediment out to the marine, and at other time periods for it to store sediment in the terrestrial. And because of this, you could think about going forward in time with this delta here. There are actually fluctuations in the volume of sediment that are stored above sea level, even if the supply is constant coming into the delta. There's autogenic fluctuations here. So we looked at these autogenic fluctuations in the lab. We're actually able to measure the size of these autogenic fluctuations of the volume of sediment that's stored above sea level in our experiments. And with this knowledge here, we created two dimensionless numbers that are going to help us think about signal storage. One here is related to the magnitude of a sediment supply perturbation, and we're going to normalize that by the largest autogenic perturbations in the change in the volume of your delta over time. If you take a volume and you analyze how that volume is changing over time, that actually gives you units of a sediment supply. So we're normalizing our sediment supply signal by an autogenic magnitude. And we're going to normalize the period of a sediment supply signal here by a time scale of the autogenics, our friendly here compensation time scale. So what this allows us to do is create a diagram here where we have the time scale of a sediment supply perturbation on the x-axis and the magnitude of a sediment supply perturbation on the y-axis. And what we can do is figure out a curve here that represents a signal storage threshold. This storage threshold is related to the size or the magnitude of the autogenics going on at different time scales in the basins. And if your signal is smaller than the size of the autogenics at a given time scale, we are predicting that you cannot, or we hypothesize that the signal gets shredded and not stored in the record. Whereas if the signal is larger than the autogenics, it gets stored in your stratigraphic record. Each of these symbols is an experiment that we've run that has right now confirmed our hypothesis, right? So if you're above this, this transfer threshold, signals get stored. And we can look at this in a number of different proxies in the record, whether it's sort of thinking about the size of your deltas and how the delta might have shorelines that transgress or regress during sediment supply cycles, or changes in the transport slopes of the deltas that are affected by the sediment supply. And we basically find that these autogenics here dictate whether or not a signal gets transferred. I'll just note on here that our PETM might be occurring over a time scale in many sedimentary basins that is 2, 3, 4 times the compensation time scale. And so for this, basically, as long as we have as long as we in the PETM have a change in the sediment supply that is larger than the autogenics, it should get stored in the record. For our experiments, this roughly means that if the sediment supply during the PETM changed by maybe about 50%, it would get stored in the record. Okay, so that's sort of the take home of this is autogenics can control the storage of information like sediment supply cycles coming into the basin, but you need to think about the time scale of the event and the magnitude of the autogenics. Okay, I've just got a couple final points that I'm going to make here that are much shorter than what we've gone through before. And the last sort of real big point that I want to talk about here is changes in not only maybe the mean sediment supply coming into a basin, but there are other ways that the environment can record a change that maybe don't have to do with the long time scale averaged aspects of the routing system. Here, I'm going to emphasize discharge variability, maybe in deltaic environments. Think about this as the magnitude and frequency of floods in a basin. There's good evidence in a lot of PETM basins that in addition to climate changing and maybe sediment supply changing, the long-term sediment supply, there was also maybe a change in the extremes of your precipitation events. And maybe that is linked into why we have coarse sands deposited during the body of the PETM. So we explored this in the lab, and I've done this with Eric Barefoot, a student of Jeff Nitrauer's at Rice. And again, one of the things that was noted in the PETM is the pre-onset and post-PETM strata is relatively muddy, but the strata during the PETM is relatively sandy. So what we did is we altered the hydrograph in our experiments between periods with small floods to periods with large floods. And we also looked at in an effect of how quickly these transitions happened. And so I'm going to close here just with a movie about this experiment that we're working on the data with now. In this movie, we start off with the system evolving with low magnitude floods. This plot here, in essence, is the size of the flood discharge relative to the base flow. You can sort of see it, maybe on the video, you might see it flickering, and that actually is the floods coming through in the experiment. So you can see we transition to these large magnitude floods, and when we do, some of the observations that we make are that the transport system moves really, really rapidly, and you get much wider, less deep channels that evolve on the surface. All of this impacts what we have that's left behind in the stratigraphic record. Okay, so in this experiment, the red sediment is coarse, the white is the fine. And what we find here when we cut the strata at the end of the experiment is that we have alternations between relatively muddy periods with isolated channel bodies when the floods were small, and we have really coarse strata with no isolated or limited isolated channel bodies when the floods are very large. So maybe that's some of the signal that we're picking apart or we're seeing in these PETM records. Okay, so it's just a bunch of different ways to think about how autogenics impact the fidelity of the stratigraphic record. Hopefully people enjoyed this. I'll finish off with just a note here about where we are, whether all this work is pointing towards the stratigraphic record being a great archive of information or a poor archive. Is the glass half empty or half full? Recently, I saw something on social media with a glass that was half full saying in COVID years, maybe the glass is just half filled with poison. Who knows? Hopefully most years we won't be in COVID though. And I'll be able to see people face to face at these types of luncheon events. For me, I sort of view the glass as completely full, half filled with water and the rest of it's filled with air. What we have here for the stratigraphic record is, we've got some limitations to the record that are imposed by our autogenics. But the good news is that we're starting to quantitatively figure out how to predict what the fidelity of the record is, which will help us better pose questions that we might want to ask of the record of Earth's history. So with that, I'll close, and I will be happy to take any questions that people might have.
Okay. Well, thank you very much, Kyle. That was really awesome. And just as an editorial comment, every time I see one of Kyle's talks or read one of his papers, I have to think quite a lot about anything I've ever thought about the stratigraphic record. And I think that's a really healthy thing. And we should all be very cautious, especially when we're interpreting how time is represented. So with that, are there any questions that anybody would like to ask Kyle? We're a little short on time, but I think we're supposed to end in about a minute. But if Kyle is willing, we can hang in there for a few minutes if people have questions. So
sorry, I ran a bit long.
No, it's okay. Please feel free to ask questions. Kyle, do you see the website with the question?
I do not have it open. I wasn't able to log in during the talk.
Okay. There are no questions that have popped up yet. Why don't we just hang in there for another minute and see what happens? And I guess I really I'll just comment while we're sitting here. I really like the timescales argument about how to see autogenic versus allogenic questions. And there's been some work on the quaternary that really supports that. I think that point is also made by Alessandro Amorosi, who would argue that when there's really strong forcing, we really see the record pick up that forcing, but when the forcing is weak, like in the Holocene, we just don't see it very much.
Yeah,
it's totally dominated by autogenics, and I think one of the challenges is trying to understand that maybe during a time period where we can actually date a lot of things. So we should talk sometime about the Holocene.
Yeah.
Okay, there's a few questions now. How about the rock record in deeper parts of the basin, not fluvial deltaic parts?
Yeah, it's a great question. So due to sort of the experimental basins that we have in the lab, we often in my lab work with fluvial deltaic systems. I as well, I do some experimental work with deep water systems. But even though a lot of these experiments are pitched or shown as fluvial deltaic systems, the concepts that we have from the experiments carry over to other environments. And the concept that I want everybody to think about is that compensation timescale, where really all that we're talking about is some roughness feature that is sweeping across a surface that is in long-term aggradation. And so that roughness feature in the deep marine might be small ripples that are existing from currents at the base of the ocean, and your aggradation rate might be much, much, much slower than on the deltaic setting. So it might actually be that you have similar compensation timescales in deep marine settings. Even though your roughness features are smaller, your aggradation rates are much smaller. And so the key thing here is to, I think with what I'm trying to tell everybody, don't get focused too much in the environment of deposition that I showed. Focus more in on the concepts of thinking about roughness features that are scouring over a surface and what that might mean for the incompleteness that is produced by that scouring of whatever your roughness feature is.
Okay, great. I'm being told that we are going to have to wrap up after that question. So I'd like to just, on behalf of everyone else, say thanks to Kyle for a great talk, and I believe this will be available for viewing afterwards, and I'd urge everyone to take that opportunity. I'm going to try and get my class to watch the talk. Cool. And so without further ado, Kyle, thank you very much on behalf of SEPM. I really appreciate you coming, and going to your office to give a talk to an international audience. That's pretty cool, huh?
Yeah. Thanks for your service, Mike, and hope to see many people in person sometime soon.
Okay. Thanks a lot, Kyle. Bye-bye.
Bye.